So hello everyone, welcome to the CMSA Topological Quantum Matter Seminar. Today we are very glad to have Amanda Young from the UIUC to tell us roughly status gaps. Yeah, please go ahead.
All right, so thank you very much for the opportunity to be here today. I'm very happy to be able to share with you this work I've been doing over the last couple of years, jointly with Bruno Nachtigale and Simona Warzel. There's kind of 4 works that have been published that are out there, but the talk will predominantly focus on the latter two works. But kind of the motivation for what we ended up doing came from the first 2. So all 4 will actually be discussed in some way, shape, or form. So the talk will be structured as follows. So I'll give you a little bit of background about the Haldane pseudopotentials and the main properties and conjectures we expect these Hamiltonian models to exhibit. We'll actually be working with even though these are models for 2-dimensional systems, we'll be working in the second quantized formalization, which actually transforms the model into a 1-dimensional lattice model. So I'll make sure to introduce that. And one issue with this problem, we're interested in talking about spectral gaps, and one particular issue for proving spectral gaps for these models is that they have long-range interaction terms. And this actually presents an interesting challenge for proving spectral gaps. And so as kind of a stepping stone towards trying to analyze these models, the full model, we decided to first look at truncated versions of this model. So I'll introduce these truncated models, and we'll discuss how we actually see edge modes present in these models, which presents a second issue for proving spectral gaps. And the main result will be how we were able to avoid these edge states for these truncated models. And the remainder of the talk will be focused on the actual bulk gap strategy and how we were able to circumvent these edge modes. And in particular, part of the reason we were able to do this was that we were able to identify an abundance of invariant subspaces for these truncated models. And we were able to specifically separate out the ground states and the edge states into different invariant subspaces. And this was key for our bulk gap strategy. So to give you a bit of background about the Haldane pseudopotentials, these were actually first introduced as Hamiltonian models for the fractional quantum Hall effect. So the physical system we need to keep in mind is that there's some 2-dimensional manifold on which charge degrees of freedom are interacting, and that there is a perpendicular magnetic field acting on the manifolds. And Hamiltonian models theoretical models for the fractional quantum Hall effect date back to Laughlin's famous ansatz for the many-body ground state wave function. And shortly after Laughlin's introduction of his wave function, Haldane introduced this family of pseudopotentials as Hamiltonian models. And each one is tailored specifically to have Laughlin wave functions as maximally filled ground states. And these Haldane pseudopotentials are defined by projecting a repulsive short-range radially symmetric parapotential onto the lowest Laughlin level associated with the particular geometry we're considering. And so the value P that we have for the pseudopotential is specifically related to the number of times we have the Laplacian acting on the delta potential. Now, originally, Haldane pseudopotentials were only introduced for odd integers P. However, later it was realized that for even integers, which correspond to bosonic models, are also of interest for studying rapidly rotating boson gases. And in particular, all of the results that I talk about today, which will be for the 1/3 filled model, which corresponds to P equals 1, also hold for the 1/2 filled model, which corresponds to P equals 0. These Haldane pseudopotentials have been conjectured to satisfy all of the characteristic properties of the fractional quantum Hall phase. And in particular, these properties are supposed to be robust under the choice of particular 2-dimensional manifold that we're considering. So a particular strategy for trying to prove that these models satisfy these properties is to consider your favorite geometry, which for whatever reason might make the calculation easier, and try to first prove the conjectures there. And for us, this is going to be the cylinder or the torus geometry. Either situation works. I'll focus on the cylindrical geometry in this talk, but our results do extend also to the toroidal geometry as well. So what are these properties and conjectures we would like to see exhibited in the Haldane pseudopotentials? Some of these have already been proved to be exhibited, but the spectral gap conjecture is still open. So just to give you some notation, we're going to let lambda represent our physical space, so the actual manifold that we're working on. N will be the number of particles that we have in our system, and the filling factor nu will just be the ratio of n to the volume lambda. And we will be working in the second quantized version of the Hamiltonian. So even though I introduced it in the first quantized formula on the previous slide, I will introduce the conjectures and properties in second quantized form. So the first thing we expect is that number one, there's going to be zero energy ground states. The Haldane pseudopotentials are necessarily non-negative, so the zero energy states will correspond to our ground state space. And we expect that our zero energy states will have a maximal filling. And the filling that we'll have is specifically corresponding to the value of P. So for P equals 1, the maximal filling of any ground state will be 1/3. And in particular, what is known is that the Laughlin wave functions do actually constitute a maximally filled ground state for the Haldane pseudopotentials. We also expect there to be spectral rigidity. So if we thought about increasing, we fix the volume lambda and we increase the number of particles in our system, so maybe we go beyond this maximal filling for a ground state, we could ask what is the lowest energy in that particle sector. Well, what we would expect is that the lowest energy is going to grow like some function that's increasing in the filling nu. And in particular, for the rapidly rotating Bose gases, this is related to the Uras line. And we are actually able to show that for our truncated models, we have this sort of spectral rigidity. Now, the majority of this talk is going to be focused on the spectral gap conjecture. And so what we expect here is that there is, if we look at the finite volumes lambda and we think about letting them tend to the thermodynamic limit, that the spectral gap above the ground state energy will be strictly positive. So here we're looking at vectors psi that are orthogonal to the ground state space. And we're looking at the minimal energy in those sectors. And in particularly, this gap, it should also imply the incompressibility of the fractional quantum Hall fluid. So in particular here, what we should keep in mind is the idea that there's two ways to change the filling. One is to include new additional particles into the system, but another way would be to compress the actual system, the volume lambda. And if we compress the finite volume lambda sufficiently far, what we would see is that at some point in time, there'd be some critical value that we can't compress any longer and stay within a ground state, that we would have to jump into an excited state, and then we'd have a discrete energy jump. So this actually will imply the incompressibility in the system. And Nicolas Rougerie has a nice discussion about this in a paper that he published in 2019. And finally, beyond the spectral gap conjecture, we want to talk about also low-lying excitations. So above this ground state energy, what kind of ground states do we have, and what kind of excitations do we have? And we expect to see anionic excitations. So these are the four things we think that should be exhibited by the Haldane pseudopotentials. And in particular, we would like to focus on the spectral gap conjecture. And what we would like to do is not consider the full Hamiltonian, because again, there's going to be these long range interactions, but a truncated version of this Hamiltonian. So if this truncated version faithfully represents the full Haldane pseudopotential, we would also like to be able to recapture all four of these properties in the truncated model as well. And that is what we've been focusing on in these projects, with an emphasis on the spectral gap conjecture. So just to recap, we're going to be looking at the Haldane pseudopotential in the cylinder geometry for the 1/3 filled model. In this case, the Hamiltonian, or the Fock space associated with the system, is the fermionic Fock space generated by the lowest Landau level associated with the vectors for this geometry. And one thing specifically to note about the orthonormal basis for this one particle Hilbert space is that the index k that we use here for the vectors actually corresponds to where the functions are localized to along the cylinder. So the wave function is proportional to a Gaussian, and in particular where the Gaussian is centered is corresponding to discrete spaces along the lines. This lattice that we're going to see coming out from the second quantized version, we should think about each site as corresponding to a single mode from the lowest Landau level. And this does correspond to where a particle is localized in space. So for the nu equals 1/3 model, when we write the Haldane pseudopotential in terms of its second quantized formulation, what we end up getting is a sum of non-negative operators that are indexed by a half integer z, and this half integer should be thought of as some center of mass. And the operator that induces this positive term can again be a sum of over integer or half integer terms. Whether it's integer or half integer just depends on whether or not s is integer or half integer. And it's going to be a sum of annihilation operators that corresponds to the Laughlin state, or the Landau state, excuse me, associated with the site s plus k and s minus k. So here k is thinking of as the distance you are away from the center of mass. And the coefficient here, what we see, decays x, like a Gaussian again, in this distance k. So it's not unreasonable to expect that if we were to take this operator bs and truncate it to only the first few leading terms, that we would produce a Hamiltonian that should well represent the true Haldane pseudopotential. And that is exactly what we did. And the truncation we took corresponded to taking the values of k, this distance being at most 3/2. This truncation was first introduced by Janssen and Nakamura, Wing, and Bergholz in 2011, 2012. And when you take this truncation, you end up with two types of terms. The first corresponds to when s is integer, and it will produce for you an electrostatic term when particles are occupying next nearest neighbor sites. And the second is a dipole hopping term that corresponds to the energy that's produced by taking particles that are next nearest neighbors and hopping them to being 3 sites away and vice versa. So this here will give us our two types of finite range interaction terms that we'll use for the truncated model. So now not only do we have a finite range interaction, but now I want to talk about the spectral gap question associated for this finite range interaction. And for quantum lattice models, the typical approach for proving spectral gap, proving a spectral gap in the thermodynamic limit is to consider finite volume systems, and then to consider the gap for a finite volume system and try to prove uniform lower bounds as we let the system size grow. So even though this Hamiltonian was originally created for the infinite cylinder, we're going to now consider also truncating our cylinder to just a finite region of space. And that will be how we get the finite volume truncated model. So in this situation, we're going to consider a finite cylinder over some interval in the one-dimensional lattice Z, so from A to B. And in this case, the Hilbert space, which would correspond to the Fock space, we're going to use instead the occupation states to represent the orthonormal basis. So these will be kets of 0s and 1s, which correspond to whether or not the Laughlin state at site K is or is not occupied. So 0 being unoccupied, 1 being occupied. If we generalize the coefficients that I had on the previous slide for the finite range interaction, this will lead to the following finite volume Hamiltonian with open boundary conditions, where I will have now two parameters that are producing the Hamiltonian, the hopping parameter lambda, which I take to be some complex value, and a parameter kappa, a coupling constant kappa that's strictly positive. And here it's a sum of, again, of two terms. The first is the electrostatic term created from the choice of having center of mass being an integer value. And the second is the hopping term from the half integer center of mass. And so this corresponds to the energy from taking particles that are next nearest neighbors and hopping them to be 3 sites away and vice versa. This Hamiltonian has two types of symmetries. It's particle number preserving, and it also preserves the center of mass, which in a cylindrical geometry you should interpret as the conservation of angular momentum. And if I do want to make contact with the coefficients that I had on the previous slide for the interaction, in the physical regime from the original Haldane pseudopotential, one would take kappa to be this value and lambda to be this value, where alpha here is the ratio of the magnetic length to the radius of the cylinder. Now, these parameters are going to be important because it's going to be in a particular limit of these parameters that we're going to see these edge modes appearing that are going to give us some issues for proving spectral gaps. And that limit is the tau-Thouless limit. So if we think about taking the radius of the cylinder and sending it to 0, in the physical regime, I would have kappa would be a robust order 1 parameter, and lambda would be tending to 0. And lambda tending to 0 is going to be the key quantity that we're going to look at for identifying these edge states. All right, so our goal now for this Hamiltonian is to prove a uniform gap that's independent of the system size lambda, so the length of our interval from A to B. So our goal is to show that for any value L, which is the length of our interval, there exists some gamma that's strictly positive, that if I look at intervals that are longer than length L, the spectral gap above the ground state energy of the Hamiltonian is lower bounded by the constant gamma. Where here the gap again is the difference between the first excited state energy and the ground state energy of the system. And here the fact that I'm emphasizing that the Hilbert space is H lambda just means it's the minimal eigenvalue amongst the whole Hilbert space. Later on, we're going to be restricting to subspaces, and so this notation here is just meant to emphasize it's the lowest energy in which subspace. Now sorry, yes?
Yeah, may I ask one question here?
Absolutely.
Yeah, so we know the laughing state is the exact ground state for V1 interaction if there's no truncation. But if you truncate the Hamiltonian, the ground state is not necessarily exactly at 0 energy, right?
So that's a good question. So let me say a couple of things. So number one, for this particular model, you can show that the Laughlin state is still a ground state, but that this truncation does not destroy that for this particular truncation. Mm-hmm. But there are other truncations you can take that you will still have. So let me say two things. You will still have 0 energy eigenstates. For example, that no matter which truncation you take, as long as you take the truncation of the BS term to create a new positive operator, you will always have, for example, the vacuum state in your trivially as a ground state. But what you will not necessarily have is that the maximal filling of the ground state will be preserved. So that is something that you have to be careful about. Mm-hmm. So it's not that you won't have 0 energy ground states, but that you won't have the correct filling. So you won't have that you're preserving the properties that you expect to be preserved for the fractional quantum Hall effect.
I see. So let me clarify if I understand correctly. So you're saying sure. On the sin torus, let's say if we don't do any truncation, Laughlin state is the equal 0 ground state. So
it will, yeah.
Yeah. So that's the V1 pseudo-potential. So now if we truncate some long range interaction term, you're saying that the ground state is still at 0 energy.
There is a 0 energy ground state, yes, this is true, but like the filling will change, which is kind of a weird thing. So if you were to restrict to the 1/3 subspace, it's not guaranteed that you will have a 0 energy state in that subspace. So I think Popich did some work on this, and he was able to show that if you take longer range truncations, it comes back to being 1/3 filled, but it depends on the truncation you take. So that's just some numerical evidence that he has. So whether or not there are specific truncations that preserve the 1/3 filled factor beyond the one that we considered, that's an open question.
Mm-hmm.
Yeah.
So in the next slides, in the last equation, you set E0 to be 0 is because you also allow the filling to vary.
So in this particular case, and we will see this later on, the maximal filling of this ground state is 1/3. So yes, but you can allow for this filling to vary, and I do want to allow for that in particular. That will be important for the uniform gap conjectures in particular, because even if you have a 1/3 filled state, when you take these finite volume truncations, if you think about like some infinitely filled 1/3 state, If you take a finite volume truncation of that state, it may not be that that state that you create is actually 1/3 filled, but it's still part of the ground state. So you do want to allow, I think, for lower fillings in your ground state space, in particular, just for how these gap methods work.
Okay, thank you.
You're welcome. All right, so again, the ground state gap that we're looking at is the difference between the first excited state and the ground state space. And as I said, we will see that the lowest energy is 0, and that is attained by a 1/3 filled state, including the Laughlin state. The Laughlin state is a ground state for this model. All right, so the uniform spectral gap. So we have the uniform gap, even though we want the gap to be positive in the system size lambda, it's going to depend on the model parameters that we choose for the Hamiltonian. So this gap will depend on kappa and lambda. And in an initial work with Bruno Nachtigall and Simona Warzel, what we were able to prove was the following lower bound on the gap for the Hamiltonian with open boundary conditions. We were able to show that there was some constant that was order 1. It does depend on the two model parameters, but it's order 1. So that if we took our hopping parameter lambda to be within a certain range and our length of our interval to be sufficiently long, the gap of the Hamiltonian for length L could be uniformly bounded from below by this constant, the minimum of the spectral gap, and then times the minimum of the spectral gap for some finite volume Hamiltonians where the values k are between 7 and 9. Now, if we actually analyze the gap numerically for these small short range finite volume Hamiltonians, what we see is that the gap for these finite volume Hamiltonians is order of the size of lambda squared. So if we look at the numerics here, which is the Hamiltonian for on 9 sites, as we think about this is the x-axis here is the lambda axis. As we think about letting lambda tend towards 0, what we see here is that the gap above the ground state actually converges to 0. However, if we look actually at the Hamiltonian when the hopping parameter is turned off, which is this tau thales limit, we do get a robust order 1 gap. So even though the gap is unstable, once we actually reach this critical point, we do get an order 1 gap again. And in fact, we were able to show that this gap, this kind of order of energy for the gap was actually tight for the open boundary condition system. And we were able to show that there are invariant subspaces where you will have exact eigenstates of the Hamiltonian that have energy order of lambda squared. And one example of such an invariant subspace can be found in the span of these two configuration states, where at the left-hand boundary of the system, I have 3 particles, and everywhere else, I have no particles. However, if we think now about taking the thermodynamic limit, which corresponds to taking this interval lambda to the full integer lattice, these 3 particles that are situated at the left-hand side of the system will disappear, and this will actually converge to the vacuum state. And the vacuum state is always a ground state of the system. So this is part of what suggests to you that these states that are creating this low energy system are actually edge states. And even further evidence for this comes from when we analyze the spectrum for the Hamiltonian with periodic boundary conditions, because we do not have this instability of the gap. If I look now at the spectrum of the Hamiltonian on 9 sites where I impose periodic boundary conditions, and I think about taking the parameter lambda tending to 0, the gap remains robustly order 1. So this is also suggestive of the fact that these low-lying energies are only due to edge states. And so therefore, we would probably want to, instead of getting a uniform gap for the model with open boundary conditions, we would prefer to get a uniform lower bound on the gap for the model with periodic boundary conditions. This would probably give a more accurate estimate on what the bulk gap is in the thermodynamic limit. So that is what we tried to do next. However, what we ended up finding is that when we produce this lower bound on the gap for the model with periodic boundary conditions, we again still got a lower bound that was order of lambda squared. And so this was not what we expected to find, but after we sat down and we thought about it for a minute, we actually realized that this is exactly what we should have expected to happen, and it had nothing to do with the physics of the system and what should have actually happened in the system, but rather this was a byproduct of how spectral gap methods actually work. So the idea of a spectral gap method, is that we want to be able to produce a lower bound on the spectral gap of some larger system that's independent of the system size. Now, in practice, how this actually works, though, is that we want to think of a short-range interaction. And in that situation, we expect that these low-lying excitations cannot occur at distances that are too far away in space. And so in particular, if we can localize in the system the region or the area where a local excitation can occur, the idea of a gap method is to use the spectral gap of the Hamiltonian for the subsystem to get a lower bound on the gap for the larger system. But even if we impose periodic boundary conditions on the larger system lambda, the subsystem that we actually localize the excitation to is going to naturally have open boundary conditions. And so if the model with open boundary conditions have edge states, even though we know that these don't persist into the model with periodic boundary conditions, the estimate that the gap method will produce will be one that still reflects the presence of these edge states because they exist for the model with open boundary conditions. And so this presented a challenge for how do we actually now still use a finite volume system to estimate and get a uniform lower bound on the gap for a model with periodic boundary conditions, but we do it in such a way that these edge modes aren't detected. And so that's what we were able to achieve, to solve and overcome with our bulk gap strategy. And the result that we were able to prove for the truncated 1/3 Haldane pseudopotential was the following. We were able to show that if we take any model of the hopping parameter, that there's some function that if we take the modulus of the hopping parameter squared and plug it into the function, if that thing is less than 1/3, then we get the following lower bound on the bulk gap. And the point to really keep in mind here is that to remember that kappa is some order 1 parameter, and that if we take the limit of the modulus of lambda heading towards 0, this estimate that I have here remains robustly order 1, as does this estimate here. And this function f that we have, it is explicit. I can write it down. However, it's, I think, a bit more illustrative to give the graph of the function, which shows that this is a decreasing function. So in particular, as lambda goes to 0, this quantity here actually goes to 1. So the main take-home message here is that the bulk gap still remains open, even though we have these edge modes in the finite volume system. And on top of this, whatever I'm going to talk about today, you can actually generalize it to the also 1/2 truncated bosonic model as well, which bosonic systems have their own challenges for proving gaps, but this particular Hamiltonian is quite nice. And so the types of techniques that we use here also translate over to that model as well. Okay, so what is this bulk gap strategy? Well, the idea is actually quite simple and elegant. All right, so here is the idea. So let's suppose that we have the Hamiltonian, and here this hash, this pound sign notation is just going to correspond to either taking open boundary conditions or periodic boundary conditions. But for the moment, let's just think about this as being the periodic Hamiltonian. So the issue here is that the edge states are being detected by the spectral gap methods. So what we would like to be able to do is to take the ground states of the system with periodic boundary conditions and separate them from the edge states for the open boundary condition system. And if we can find 2 invariant subspaces for the Hamiltonian that separate the 2 systems, then what we can do is we can use what we will be able to do is block diagonalize the Hamiltonian into 2 terms. The first being a block of the Hamiltonian that contains all of the ground states. The second being a block of the Hamiltonian that contains all of the edge states. And so to produce a lower bound on the spectral gap for this Hamiltonian, then it corresponds to now 2 calculations. Number 1, finding the spectral gap of the Hamiltonian in the first block that contains all of the ground states. So what is the first excited state when I restrict the Hamiltonian to the subspace? Now in the second subspace though, I don't have any ground states. Every eigenstate of the Hamiltonian is actually an excited state for the full system. So in the second subspace, what I'm actually trying to do is get a lower bound on the minimal energy of the system. And the point here is that to produce a lower bound on a ground state gap versus a lower bound on the ground state energy, these are two different types of calculations and the techniques are different. So while I will still apply spectral gap techniques to the first subspace, in the second subspace, I will apply techniques for producing a lower bound on a ground state energy. And now you can see why this sort of strategy will produce something meaningful, because when I apply the ground state energy gap methods to the first system, there are no longer edge states in the system for the spectral gap methods to detect. So the estimate that I get on the gap in that subspace is going to be is not going to reflect the presence of the edge states. For the second system, the lower bounds that I produce for a ground state energy do not necessarily require me to consider subsystems of the Hamiltonian. So that means like subsystems of the physical system. And so if I do not need to use methods that require me to consider subvolumes, I will again not detect the edge states of the finite volume system. And so the result here will be a lower bound on the gap of the Hamiltonian that is invariant of the edge states. Okay, so then the question now becomes, can I identify what these invariant subspaces are that separate the ground states from the edge states? And that is the majority of the work that goes into this. On top of that, for the first calculation, for calculating the ground state energy gap in the first subspace, it is also very helpful to have a good description of the ground states themselves. So a lot of the work to identifying this invariant subspace corresponds to also identifying what the ground states are of the system. So we will be doing both things kind of at the same time. All right, so now the goal is really to construct these invariant subspaces and the ground states for the Hamiltonian. Now, this Hamiltonian is what is called frustration-free. It is a sum of non-negative terms. And in particular, the ground state space is given by the zero energy eigenspace. So because this is a sum of non-negative terms, what that means is that the ground state space is given by the intersection of the kernels of the individual interaction terms. So we are trying to construct vectors that simultaneously are in the kernel of each interaction term together. So now if we let mu correspond to a generic configuration state, we want to ask ourselves what is required for these states to construct something that is simultaneously a zero energy state for each interaction term. Well, in particular, the first part here are these electrostatic terms. They give an energy penalty if you have two particles occupying next nearest neighbor sites. So in fact, the configuration states themselves are actually an eigenbasis for the collection of electrostatic interaction terms. And in particular, these configuration states are ground states if and only if the occupation at two next nearest neighbor sites is not of two next nearest sites are not occupied at the same time. So the product of the configuration is equal to 0. So really the difficult terms for constructing ground states come from this electrostatic hopping term, which remember is a sum of two terms that will destroy. So the hopping is Q star Q, where the hopping will take particles that are next nearest neighbors and hop them to being 3 sites away. And so this electrostatic term only acts on trivially on an interval of length 4. So if we consider configuration states on an interval of length 4 and how this hopping term can interact, it's very easy to argue for yourself that if the filling or if the occupation on this interval of length 4 is greater than 2, that you'll necessarily have an excited state. If it's less than 2, you'll necessarily have a ground state. So it's only at filling equal to 2 where you might have both an excited or a ground state. And the ground state of interest here is actually going to be the one that takes the terms that are 3 sites away and hops them to being next nearest neighbor. And you can actually construct from this an exact ground state. Now you can take these two observations here, and you can use this to construct an actual invariant subspace of the Hamiltonian. So if we start now from taking a configuration that just repeats the pattern 1, 0, 0, this corresponds to having this first term here from the hopping term. You can construct an invariant subspace of the Hamiltonian by thinking of this pattern as 1, 0, 0 as being some sort of domino tile, which I'll call a monomer. And anytime I have 2 neighboring monomers, I'm going to replace it with what I call a dimer tile. So it gets these 2 tiles get replaced with a single tile where I hop the 2 particles to being next nearest neighbors. And if I start with this configuration of just tiling my lattice with monomers, and I take all of the configurations I can construct by doing this tile replacement, that will create for me a collection of configuration states that, when I take the span of all of these configuration states, actually generates an invariant subspace of my Hamiltonian. And moreover, it contains a single ground state. And that single ground state corresponds to how many of the particles I have hopped to being next nearest neighbor pairs. And that ground state will correspond, or that the coefficient in the ground state will correspond to how many pairs I've hopped to being next nearest neighbor. And the pairs that I've hopped to being next nearest neighbor correspond to how many dimers there are in the tiling. So the specific ground state for this configuration that I started off with will be the sum over all of these configurations, which I call tiling states. And the coefficient in front will just be lambda to the number of dimers in the tiling. All right, so this collection of configuration states was generated from this first state here, which I'll call a root tiling. And the generation of all of these tiling states just correspond to these replacement rules. So in principle, this is how I can get one ground state. It will be a maximally filled ground state, but there are other ground states I can get as well. And this can correspond to, for example, separating out monomers with additional vacant states. So if I want to construct all of the ground states for this Hamiltonian, I can do a very similar procedure. I just have to introduce some additional tiles to the mix to be able to create the full, to create all of the ground states and all of the invariant subspaces. So I introduce also a void state, which corresponds to just an unoccupied states. And then I have some boundary states where I have various left and right tilings, and this just corresponds to taking truncations of either the monomer state or the dimer state that I had on the previous slide to fit at the boundary as well. Now, as long as I have the left tiles on the left side of the system and the right tiles on the right side of the system, I can otherwise place monomers and voids anywhere in the system. I can also have a monomer or void at the very left boundary. This is perfectly fine. But the point is that all of the root configurations I can create have to be constructed out of these tiles. And then again, how I create all of the configurations that span the invariant subspace is just via a replacement rule, where any 2 neighboring monomers can be replaced with a dimer. And here, these right 2 tiles that only have a single particle, those are also considered to be monomers. So once I have these tilings and I create these invariant subspace, this collection of configuration states via this replacement rule, I can again argue that this collection of states will span an invariant subspace of the Hamiltonian. It is indexed by the root tiling, and this root invariant subspace again supports a unique ground state. Moreover, you can prove that this actually is all of the ground states. And so the invariant subspace of interest is going to be the direct sum of all of these tiling states that are indexed by the root tilings. You can do something similar for the periodic boundary conditions. The only difference here is that we do not have any edge states or any edge tilings. So we only have the monomer and void to construct the root tilings. But we again have a similar replacement rule where two monomers can be replaced by a dimer. But again, we'll be able to construct all of the ground states for the periodic model in the same fashion. So there's two things to point out. Number one, the dimension of the ground state space is actually exponential in the system size, which this can cause some issues for proving proving a uniform gap. However, the fact that we have this collection of invariant subspaces will actually save us in the end and will be able to help us prove the main theorem. And the second is that you can see that yes, indeed, that the maximal filling of any ground state is going to be 1/3. And in particular, if your system size is divisible by 3, you'll have exact ground states with filling 1/3 factor. The other kind of key realization here is that if we take now a subsystem in our periodic model and we truncate it to a finite system, that the tilings have some sort of nice isospectral relation in that when I truncate a tiling here, I will actually get a tiling for an open boundary condition ground state. So the restrictions will necessarily give us tilings that we identified for the open boundary condition system that I saw 2 slides previously. And why is this important? This is important because it actually is going to allow us to verify that all of the edge states are not contained in the tiling state for the periodic system. And the way I can see that is again using tiling. So I can actually construct all of the subspaces that contain all of the edge states. And the key difference here is that I get to use all of the same tilings that I had from the previous system for the ground states. However, I have to introduce 2 edge state tilings now. And these edge state tilings, how they are constructed is by taking the boundary tiles that correspond to either a left or right dimer on the boundary, truncating off this last 0, and then appending on the interior a monomer. So truncating off this 0, it forces me to allow for particles to be in certain configurations that I didn't allow for in the ground states. And since the configuration states are necessarily orthogonal to each other, these tilings guarantee that any invariant subspace that I create using these tilings will necessarily be orthogonal to the ground states of the system. And in particular to this tiling spaces that I constructed previously. And so the edge states, they are again generated by root tilings. You use all of the same tilings as you did for the ground states. However, you must use one of the 2 edge tiling spaces, edge tiling tiles on either the left or right boundary of the system. So this is the example that I gave at the beginning of the talk. It uses the left boundary tile to construct the invariant subspace. All right, so once we have these invariant once we have these tiling spaces, we can now start to see how we can apply spectral gap methods to get the exact estimates on the lower bound of the Hamiltonian. So there's 3 steps in this process. We do need to consider open boundary conditions for this process. And the first step is actually to produce a lower bound on the ground state gap of the Hamiltonian with open boundary conditions when I restrict to the subspace that contains all of the ground states. In this subspace, I'm going to apply what's called the martingale method. This was first pioneered for quantum spin systems by Bruno Nachtigall in 1996. The specific form of the method that I use was a result from 2018. And the main idea here is to use orthogonal projections onto the ground state space to localize where an excitation can live. So the main goal is to produce an upper bound on operator of the following form. So here the G is the orthogonal projection onto the ground state space associated with some interval of the lattice. So for the interval of L sites, we're going to look at the following situation. If we think about acting on a vector psi, this would first project into a ground state on the first L-3 sites, and then it's going to project onto the excited states for the full system. So what this represents is we have some state of the system that is a zero energy eigenstate for the interaction supported on the first L-3 sites. However, when I consider the full Hamiltonian, I actually see that it's an excited state. So that means that by increasing the system by 3 sites, I have introduced an excitation to the system. Now that excitation does not have to be localized to those 3 sites, though. It can still propagate back. And so the question now is, how far back do I have to propagate to actually localize the excitation to a finite region of space? And my claim is that I only have to go back 9 sites to be able to confidently say that I have more or less approximated the excitation. So this is what this G here means. So the goal typically with this calculation is to take this state that is a ground state for the first collection of sites, but actually an excitation for the full system, and show that when you act with the ground state projection, when you propagate far enough back, that this norm is sufficiently small. Because being small would mean that this vector that we create with these first 2 projections is more or less orthogonal to a ground state. So therefore, it's an excited state. Now, the actual calculation here is where this function f actually comes from. And the main ingredients that allows us to actually calculate this upper bound is the fact that we actually can partition the ground states to individual invariant subspaces, and that these individual invariant subspaces are actually mutually orthogonal to each other. It is particularly here that it makes it difficult with this large degeneracy of the ground state in most situations to calculate a gap. So the fact that we do have these individual invariant subspaces that are indexed by the root tilings actually is very helpful at this particular stage in the calculation. Once we have this lower bound on the ground state gap of the model with open boundary conditions restricted to its tiling space for the ground state space, we can then produce a lower bound on the ground state energy gap for the periodic system restricted to its tiling space that contains the ground states. And the idea here is to apply a finite size criterion, such as the one due to Kanabe from 1989. And the idea here is that you can now produce a lower bound on the model with periodic boundary conditions using the ground state gap for a model with open boundary conditions. So the fact that we need this gap here is the reason why we had to do step 1. And so we were able to now produce a lower bound on this system that is more or less independent of the system size. We typically get this 1/L factor, but since we can take the ln inf of the system, this is what allows us to get the uniform bulk gap. The fact that this is independent of the system size is what is important here. Now for the lower bound on the model with, for the other subspace, we just use electrostatic estimates that are based off of more or less Cauchy-Schwarz inequalities. So the idea here is to take a vector that is orthogonal to the tiling space that includes the ground states and just produce a lower bound on the energy of the Hamiltonian. And we get 2 types of terms here. We get terms with electrostatic energy and terms with hopping energy. So for configuration states that have a positive electrostatic energy, this is simple. So we just really have to worry about here the terms that don't have the configurations that don't have electrostatic energy. But the goal here is to use the hopping term to relate those configurations back to one that does have electrostatic energy. And using that fact, we're able to get this lower bound estimate here. We do not need to restrict to subspaces, subvolumes of the lattice lambda in order to do this. We're able to do this just by considering the full system together, and the gamma the lower bound we get here is robustly order 1. So I think I'm now out of time. So let me just say that we were able to improve the lower bounds from our first work to produce a lower bound on the bulk gap that was invariant at the edge states. In particular, this will imply that for these truncated models, that the system is actually incompressible. And moreover, I didn't talk about it in this work, but we do have some ideas of the tiling spaces that would actually support the low-lying excitations. And these do kind of look like this particle, quasi-whole, quasi-particle pairs that are conjectured to be the low-lying excitations for the Haldane pseudopotentials. And numerically, this does agree for small values of lambda. So thank you very much for your attention.
Yeah, thank you for a very nice talk. Maybe can I ask one question?
So, of course.
We know in the fractional quantum Hall case, there are many gapped fractional quantum states. Some of them are exact ground state of some pseudo-potential Hamiltonians, like Laplace state, but some are not, like Gene series. So can your method apply to the states that are not annihilated by any model interactions, like generic gap to fractional quantum, like Gene series, for example?
So I don't know yet. That's a very good question. It is something that we are interested in exploring in the future and have started to think about, but I can't say at the moment in particular if it will or will not apply. But we do have hope that we could possibly apply something similar in those situations as well.
Yeah, presumably your methods can be more directly generalized to the 1/2 fermionic state.
Right. Yeah, and I think here another kind of direction is that these models have a fragmentation structure. So I think in particular these methods could also be generalized to other systems that have a fragmentation in the Hilbert space. It has a Hilbert space fragmentation. So I think that might be one thing that we want to see is like if this fragmentation, how important is it for the method? Do we need to see this in the other systems as well? Kind of that sort of thing.
I see.
It might be something, but we are curious to see if they can apply to, for example, the 1/2 state. And there was recently a paper, I think by Papix and collaborators, where they considered I think it was the 5/2 filled system. I have to double check, but they presented a truncated Hamiltonian that is also frustration free in that system.
Yeah, thank you. Do we have questions from the audience? So if no questions, let's thank Amanda again. Thank you for the talk.
Thank you very much for having me. It was very nice to be here.
See you.
See you.